All right, we're going to look here at a reaction of brass and nitric acid. This is a pretty commonly done reaction in schools. Gives students an opportunity to use some chemistry equipment, produce a really cool looking reaction. And how we do it is we also then have the students determine the amount of copper in the brass, and they use absorbance for that. So it gives them an opportunity to use a small instrument too. You're going to want to conduct this experiment in a fume hood because the gas produced, the NO2, the nitrogen dioxide, is a very hazardous gas, even in small quantities. It can cause severe lung damage pretty easily. I'm going to be doing it in a very large fume hood, so you won't really see the entirety of the fume hood, but you will see at some point. Let me try to escape the fume hood a little bit, take my phone out of there real fast. I'm going to have it elevated. You can kind of see the mesh that I have it sitting on. I don't recommend doing this elevated just in case it were to fall. You don't really want to lose control of where the gas is and the reaction's taking place. We have here at the bottom of the beaker about 2 grams of cut up brass chips. The brass chips are also coated in a polymer film, which we'll see at the end, but that's not really going to affect the results of the reaction, although in order to determine the amount of copper, you will want to do a weigh. You're going to want to dry off that film afterwards and then weigh the mass of those. That way you get the actual mass of brass involved and you don't have the polymer film included. We'll do an actual analysis of these chips at another time. This video, we're just kind of looking at the reaction. So I'm going to add 10 milliliters of 15.8 molar nitric acid. It's a very concentrated solution of nitric acid. If you used a lower concentration of nitric acid, the reaction would be slower and you would potentially also produce NO instead of NO2. If we look at the reaction that we're going to be seeing, I'll put it up on the screen here, we have copper reacting with the nitric acid to produce copper nitrate, NO2 gas, which I mentioned, the nitrogen dioxide, and some liquid water. The reaction is also exothermic, so you're going to be seeing a little bit of warming, although the bubbles being produced aren't water boiling, that's just the gas that's forming. And like I said, if you used a dilute solution of nitric acid, that gas would be NO. You might still get some NO2, but you're going to get some NO as well. And that's colorless, so it's not quite as showy as that. So let's go ahead and get this started. As soon as we add it in, the reaction starts immediately and it starts producing the very brown, very unpleasant looking nitrogen dioxide. And you can see at the bottom all of the gas being produced as the brass dissolves. Really, it's the copper dissolving and breaking apart. And you can see the benefit of doing this in a fume hood is it really carries that gas away. You also see that the solution starts out pretty green. You can kind of see the greenish color there at the bottom of the beaker. Normally we think of copper solutions as being blue when they're in water, although this one's green because of the nitrates. Because the acid is so concentrated, there's so many nitrates floating around, that the copper is going to be coordinated or basically surrounded by the nitrates, giving it a green color. If you dilute this solution, as you do in later steps in the course of the experiment, it turns a more blue that we're more used to seeing as those nitrates are displaced by the water molecules. So it's much less energetic right now, as there's a lot less solid, but it's still producing a really good amount of the gas. We'll generally consider this reaction complete once there's visually no more gas being formed, although after the first few minutes there tends to get really very light in brown, and we'll see that here in a bit. But then you're going to want to swirl it around pretty aggressively just to make sure that you're definitely getting all of it. That might not be a completely necessary step. If your metal wasn't coated in a plastic like mine is, it might be more of a necessary thing, because I think what happens is the plastic film kind of crumples up like a plastic film would do and forms little creases in itself that I suspect little pieces of the metal probably kind of hide out in, and then stirring can help with that. So you'll see that here in a bit, although we still see a little bit of the brown gas there. If we kind of look through the beaker to the white background, you can kind of see a little bit of brown tint in there. Once that brown tint is gone, then you can go ahead and grab the beaker. I still definitely wouldn't take it out of the fume hood, and then you can do some swirling of it. You can see it's already a little bit more blue, although it'll get much more blue, much more of a nice little blue color of copper solutions later. So you see as I swirl it a lot here, you can kind of see some of the brown gas coming out still. Yeah, that's why you're going to want to swirl it. When I have students do this, I usually, if we have time, I have them do it one at a time, and if we have time, I just have them do it, and then do this first, and then as they prepare all the other solutions that they're going to need to conduct the experiment, we just let it sit. So it sits for like 20 or 30 minutes, depending on the student and how quickly they get done with the other stuff, and that's generally enough time, and you don't usually have to swirl it at that point. But yeah, just here and trying to get it done in just a few minutes, you're definitely going to want to swirl it quite a lot. And then there we see the polymer film that's left over. There's no metal left over, it's just the shadows of the polymer film. The polymer film is, like I said, it's there, it's on the brass. I suspect that it's there to prevent against corrosion or something. I'm not totally sure, but yeah, it doesn't really interfere with the reaction at all, which is kind of a testament to how durable some of these plastics are, that they're able to just kind of sit there in this really strong acid and not do anything at all.